Okay, good afternoon. My name is Jan Kerschkens. I'm the Executive Director of the newly created Center for Intelligent Systems at EPFL. It's my pleasure to welcome you to the 5th CIS Get to Know Your Neighbors seminar. With this CIS seminar series, we strive to promote exchange between researchers all over the campus. We propose a bi-weekly schedule for 1-hour seminars with 1 to 2 speakers per session. Today's seminar features a talk of Professor Alexandre Alahi of the EPFL School of Architecture, Civil and Environmental Engineering, ENAC. Please be reminded that the seminar is being recorded and will be shared online afterwards. Dear Alexandre, the stage is all yours.
So thank you again for the introduction, the invitation. I'm extremely happy to present our work on building intelligent systems. Our lab focuses on the AI part of intelligent system. And as you know, AI is quite trendy. You hear it everywhere. In fact, even the European Parliament in 2016 acknowledged that AI will affect all segments of our society. And 2 years later, they put mobility at a crossroads with a promise of having autonomous vehicle everywhere. But this is Switzerland today. And this is the future that was promised by AI. Autonomous vehicle everywhere in our daily life with self-driving cars, delivery robots coexisting with humans in the open world, changing our last mile mobility. I refer to a last mile mobility as moving humans or goods to their final destination. Optimism is very high, billions of money and the market is huge. Yet I argue that the current state of and even definition of AI is not safe and not good enough to enable this future. So if you disagree with me, you're open to challenge me and we can talk, and I'm gonna try to prove you why I think that we are not there yet. This is one definition of AI, any device or system that perceives its environment and takes action for its goal. So over the past decades, we researchers, companies, academics have focused on these two pillars, a perceiving pillar that you can even think of it as maybe a computer vision pillar, and an acting pillar to solve this problem. What's the outcome? We still have accidents. As you all know, the technology is not ready. But the interesting part is that the accidents are no more due to these two pillars. It turns out that 98% of the current accidents are due to an unexpected stop of the self-driving car, of the autonomous vehicle. And other drivers were crashing into the car. And that's not a perception problem anymore. And similarly, if you take these cars into my hometown, Paris, they fail to navigate into this environment. They cannot basically operate in cities where driving style is no more by the driving code book, such as maybe Paris, Naples, in any of our home countries. And what's missing in the current technology of AI? I claim that AI must understand social etiquettes and must learn to anticipate behaviors. In other words, social awareness is missing in the current state of AI. So let me introduce you our robot, Lumo, navigating alongside pedestrians in Lausanne. I argue that this is even harder than a self-driving car. Why? Because the environment is not as structured as the road, and the dynamics of agents around the robot, like pedestrian, has much more non-linearity than vehicles. Hence, I claim that if AI can operate our robot in this environment, in this crowd, it can operate any autonomous vehicle. We will have the methods and technology to actually control any autonomous vehicle. Yet, again, our robot is suffering to move in this crowd. It will either freeze because he is quite conservative or actually lead to an accident. Hence, again, AI must understand the social etiquette, the unwritten social rules of navigation, such as respecting personal space and what is this distance that we actually like to preserve, yielding right of way maybe, And you must learn to anticipate all these behaviors to actually be able to imitate us and move around in this environment. So let's look at a more concrete example with our robot, and let's see what these perception pillars and the planning pillar are saying. So first, following our definition, with the perception, we can detect these humans. And as I mentioned, we have done amazing progress in perception, detecting humans, detecting objects. We're quite good at it to do this. Then the acting pillar will basically identify a few paths that are physically possible and select one of them, potentially the shortest path. However, AI, again, must understand that it's socially not accepted to navigate between these two people talking to each other, although there is enough space. And it must forecast the behavior of the left person to not cross path. And there's only a single path here that is socially accepted, which is the green one. So how can we get there? I claim that we need to introduce a new additional pillar, a fundamental pillar that I call a social forecasting one, in charge of understanding and predicting human social interaction. Now, these three pillars will form what I like to call socially aware AI, a new type of cognition that is basically AI augmented with social intelligence. Social intelligence is this capacity to effectively navigate and negotiate social interaction. So I argue that if a system is powered by such intelligence, it will have the capability to imitate humans and coexist and blend in a very natural way. To prove this, beside measuring safety and efficiency, we will actually study and see if we can pass what I call the nonverbal social Turing test, asking humans whether they think our robot is controlled by humans or not. And I believe that if we can pass it, then our technology is ready to be deployed in our society in a safe and trustworthy way. So that's the big picture. And now in the lab, we have been working on each of these pillars, pushing the limits, and in fact, even rethinking how the perception and acting pillar needs to be designed and developed to enable our socially aware AI, knowing that we also need to predict the future. So let me now focus on the social forecasting pillar and what we have done into this area. So the problem formulation is quite simple, given a sequence of states. For clarity, I will represent a state as a human XY coordinate in time. We want to predict the future states, the next 5 seconds. But we have some challenges that is a bit different from other time series prediction, like financial time series or even NLP. Here, we need to model interaction with other sequences, basically social interaction. The way I behave depends on how other people are behaving. And we also have a multimodal distribution. So over the past decade, so this is not necessarily a new topic. People have actually studied this for simulation, for evacuation purposes. But they studied in a way that they did not have enough data to actually build a data-driven method. So a lot of the key contribution in this area were based on, for instance, social force modeling, which is designing a set of functions, handcrafting a set of functions that are describing an attractive and repulsive behavior between agents. Or framing this problem as a discrete choice modeling problem where you can actually, again, handcraft a set of function for your systematic term and still use the random utility maximization theory to solve this problem. All these methods are great. They are quite well studied, defined. They have a lot of interpretability, but they suffer from the prediction accuracy. They cannot actually model long-term dependency in the data and the complex interactions. So what I've decided to address all this by building, in fact, a digital twin of a train station. A train station is an amazing opportunity to collect data on human social interaction. So we have installed cameras in a Swiss train station. In fact, this is Basel and also Lausanne. Let me actually show you one of the corridor in Lausanne. This is, I think, the East corridor. Here I'm showing you the top view. We installed about 30 cameras. I like to call them sensors because at the end, it's fully privacy safe. So the data that we are using, for instance, are these depth signal from the scene and or thermal imaging from the scene. But in real time, we are actually extracting only the XY coordinate of humans in the space. And this is a visualization of the type of data that we are collecting. So we are never saving any images. In real time, we are actually extracting all the trajectories of humans in the space. We are detecting within each camera and doing the tracking across camera, all in real time. So we have collected a lot of data. And in fact, the SVB was interested in this to rethink how to redesign the train station given how we commuters are using the space. And this construction that will happen were budgeted for, I think, 800 million, yes, of Swiss money to actually redesign Lausanne train station. And they could only justify it thanks to our data. They had to show that, for instance, the density of humans in the space has reached its maximum capacity, that we are no more able to offer the right level of service to our commuters, and we need to modify the space. So to put this work into a perspective, we collected millions of trajectory. We collected data over 2 years. And this was the first time, to our knowledge, that we could actually study human interaction, human crowd dynamics at this scale. And to put, again, this work into perspective, the red dot in the slides is the amount of data that was available before. So now we can actually reproduce all the success story, all the AI success stories, such as ImageNet success story to perceive, to classify images. We can actually, now we have this data set that we call TrageNet++, where researchers can now do all this research to develop data-driven method to see if we can match human level performance. And that's what we did. So we started by designing new data-driven methods. And let me briefly share with you what we have done over the years. We first studied how to use a recurrent neural network to solve this task. And we showed that it is indeed possible to learn a representation, which I refer to it as a social representation, with a recurrent neural network architecture. And the challenge here is, again, as I mentioned, this is a bit different than a single sequence prediction task. So what we could do naively is we have all this trajectory for each person, and each trajectory can go into an LSTM, a recurrent neural network, to predict the next, to solve the basically sequence prediction task. And this is quite popular in NLP, in other fields. And we have done a lot of progress also in how to design this encoder to do good in sequence prediction. But in our case, we need to study how we can jointly predict multiple sequences that have some correlation. So we proposed some new pooling strategy, some new architecture design, such as how to pool the hidden state of multiple LSTM to jointly reason on the prediction task. So we, for instance, here on the right, you see that we can rewrite, we can use an indicator function to sum over the hidden state of our neighboring pedestrian, and we can learn then an embedding to combine it with our other inputs of our past history to then solve our forecasting task. We then also studied how to basically be robust to the multimodality distribution of our output. So we naively started by minimizing our loss function with L2 loss function. We wanted to basically minimize the prediction error, and we thought that maybe L2 is the way to go. But it turns out that nah, it definitely is losing some modes into our output distribution. So there were other multimodality losses where, for instance, the winner takes all is studying, is basically selecting the output that has the minimum L2 with respect to multiple outputs. And this is how we're penalizing our encoder, our neural network. And in this slide, Y is basically the output of the neural network, and Y hat is, for instance, the ground truth. But when you lose such a loss function, the prediction accuracy is no more good. As you can see here, I'm showing 5 modes, 5 lines that are possible output, but then the algorithm is actually predicting a lot of trajectory, and it's not actually very accurate. We decided to actually study this adversarial loss to learn the multimodality distribution, this generative adversarial network, where it's this min-max game between a discriminator trying to classify if your sample is real or generated, and the generator is trying to fool the discriminator. So we actually basically modified this GAN formulation for our task. And what happened is, indeed, we were able to get multiple modes, but we were still missing some modes. And this is quite common in GAN, and they commonly suffer from mode collapse. They have very nice sample quality, but they are not able to actually output or preserve all the modes into the distribution. So, and one common knowledge, which is in practice, it's quite difficult to learn an optimal generator. Why? Because the design of the generator might not have enough capacity. And even if we bring enough capacity, it's not here if we are able to train it long enough, given our computational resources. So what people have recently done with respect to this issue, and in fact, one of these work is from Jan, a good fellow who is behind the generative adversarial network, is at test time, basically leverage all these techniques from Monte Carlo techniques to resample basically the output. In this case, when we should reject a sample, knowing that maybe the sample is not good enough with respect to our generation and data distribution. So all these, I mean, these 2 techniques basically that I'm referring here, they were quite interesting, but they had still a lot of assumptions and limitation. So what we decided to do is we proposed to use the discriminator that has been trained, that usually we only train it offline and during training time, and at test time we discard it, but we decided to use it at test time to guide the sampling process. And we believe that throwing it away may lose valuable information. One additional motivation is that in this min-max game between a generator and discriminator, learning the discriminator seems to be an easier task than learning the generator. A discriminator is just in charge of saying yes and no. And it's potentially easier to learn yes and no than learning to generate some high dimensional signal or some signal. So we propose to use it to basically refine the sample at test time and see if basically this mechanism can help the generation process, the quality of the samples, and also the issue of mode collapse. So I'm not going to go through all these details. You can look at the papers, but the outcome was quite positive. It turns out that yes, we are able to address the mode collapse issue, and the sample quality is still quite good. In our paper submission, we naturally showed its performance in other basically toy example and other tasks to show that this is not only with respect to our problem of human trajectory forecasting. GAN are actually used in many applications. Here we are showing that we're comparing our technique with previous work. And we are showing that even in this toy example of trying to generate this 8 Gaussian distribution, we are able to not lose the modes and still have a good enough samples. We also showed that this works in higher dimensional signal, where basically the first row is images generated with a GAN, and the second row is our method, which maybe thanks to the, because of the connection, you might not see a lot of differences, but it's, we are showing the differences in the third row. It seems that we believe that the sample quality have improved. Some of these details are more pleasant to the human eyes. And basically our algorithm was able to even push further the performance of the GAN. And something that I wanted again to emphasize is what we are proposing is generic to any design of a generative adversarial network of any GAN. So it's something on top of it to basically get an extra mile with respect to the performance in using that. So this is basically what we have done. Our ongoing work into this social forecasting is basically to bring more interpretability on our data-driven method. As I mentioned, data-driven models are quite exciting with respect to the prediction accuracy, but then sometimes it comes at the cost of we don't really know what we have learned and how to interpret what we have learned. So in this latent representation, we're currently studying, can we actually disentangle some factors of variation? So for instance, can we shed light into the dimension of this latent representation, what this dimension have learned about social interaction? Can we decouple the physical law behind human mobility from social conventions? For instance, we know that we cannot occupy the same space. We cannot have collisions. But then what is this distance can be culture specific. So if we're able to disentangle this, then we can better transfer our learned model across different environments and only fine tune the components that are explicitly describing these social conventions. We have also recently studied and showed that it's possible to combine these knowledge-driven and data-driven methods together. And one of our recent work is showing that we can enhance discrete choice model with representation learning. And this got quite, was very well received in the transportation community because DCM is the go-to tool to describe all this decision-making process of humans. And here we are showing that when you use your utility function and you have the systematic term V, which is usually a function of observable variables that are well understood what they mean, and you design this function that is quite intuitive. You can also augment it with a new representation, a new term that has been learned with a neural network. And we have shown that it's possible to do it without compromising the interpretability and all the theory behind DCM. And then it opens actually very exciting avenues of research, because then you can use complex explanatory variable, complex input into a DCM framework, such as maybe not this XY coordinate, but the body joint, the raster image, or an image itself as an additional explanatory variable to be part of this decision-making process. So that's on social forecasting. And as I told you, now that we have the social forecasting, we can actually rethink the perception pillar. So the perception pillar is quite popular. It's basically computer vision, right? So detecting, I have an image and I want to extract as many meaningful information as it is. And for many years, we thought that detecting humans is good enough for self-driving car, their position. And because I want to better predict the future, I claim that no, we need to go beyond detection, but we need to understand fine-grained cues like body pose or this honest signal that we communicate. We're not necessarily aware, but you can actually anticipate our intention. Activities are also quite interesting, like the fact that we're talking to each other, or we are on the phone, or we are holding something. There is actually a very interesting set of semantics on humans, on the environment that we are interested in perceiving to, again, be able to better predict the future. And if we can better predict the future, we can better plan and have a more robust system. So this is what we have been doing, which I like to call computer vision for transportation, which is a bit different than computer vision for the internet or for images in this way. The data that we're dealing has limited resolution on the object of interest. You can have HD camera, you can have as many resolution as you want, but the human at one point will always can look very small. And what that means is that it's potentially far away, but you still want to be able to actually extract this information from limited resolution. And they also suffer from a lot of occlusion. So there's always occlusion into this data. People are behind cars, and we need to be robust to this type of challenge. Again, what's also different is the way we measure success is a bit different. I mean, we have some safety critical accuracy. There are errors that are okay and others that are not necessarily actually accepted. And we need to make sure that our algorithms are robust to these safety critical scenarios so that this can be deployed. And finally, efficiency is also a very good, a key aspect to it. We want real-time solution. We want cost-effective solution with respect to the computational resources that are available. And so we need to think of how we can solve all these perception tasks in a quite efficient way. And as I mentioned before, we are not interested in a single task, but multiple tasks. So the same potentially architecture network needs to be able to say multiple things. So what we have been doing, we have actually recently shown that it is possible to design a single neural network architecture that will output 32 tasks on, or we'll be able to understand 32 semantics on humans. It's able to actually detect them, but also extract, for instance, if they are a child, an adult, if they have done eye contact, are they moving slow? We can even actually detect their intention. Do they have the intention to cross the street or not? And technically, this is quite interesting because one way, a standard way to do it is you have a neural network, you detect pedestrian, and then for each of these pedestrians, you have another network that do each of these tasks. And almost every task can be independent. This is not cost effective, and this is not real time. We are actually digging into this type of architecture where we are showing that you can basically describe any task with field theory, with a composite field, where basically the output of your neural network at the last layer is a map where each cell is pointing to the location of your object of interest, and it's a vector pointing to where this object is with a set of property, and all this property can be all these attributes that we are looking for. And while doing that, we have shown that if you rethink your loss function by modeling uncertainty and confidence, if you're able to say in the loss function, I'm not so sure, if, for instance, you can use Laplace loss function, or you can penalize the entropy of the task, you actually get a boost. You are actually able to do better this task and do them jointly. I'm gonna actually show you some of these examples. So these are videos. I apologize if you don't see them very well. This is the output of our body pose and tracking. Here we are showing that not only we can detect the human body pose into these images, but we can also understand the 3D. So all numbers that you see here are the distance to the camera. And we have shown that you don't need LiDAR, expensive sensors. All this is based on image. So we have an algorithm that can actually solve this depth prediction given a single image without even having stereo. And we also show that how to do it with stereo. Here, I'm showing you some example of our algorithms that predict the intention of humans to cross the street. So in green means the pedestrian might not cross the road, and in blue, the fact that this pedestrian wants to cross the road. And again here, the sooner we can predict the crossing, the safer is our solution. So this is we're still not there yet, there is still a lot to do, but every second that we can save for early warning and early detection can be quite impactful in the safety of this solution. So our algorithm, we are quite excited in transportation application, but they are quite generic. So we have some requests of other collaboration where it turns out that the same technology can be used for instance, indoor environments with even 360 or camera. We have not changed anything about the algorithm. It's just use it as is. It's quite robust to these changes. Here are other domain of application where we show that we can actually solve all this problem in any image, any video. It can also be used in sports. And in fact, we have been approached by companies that they want to use our pose tracking solution because it's 10 times faster than previous work while being even more accurate. So there's a huge request even from the industry to actually deploy this solution into their systems. We also shared some tool and source code to basically model social distancing. So here this is a single we're using a single image as a monocular camera, and we are detecting humans in 3D, but also their orientation. And we believe that social distancing is not only an issue of distance, but it's also an issue of orientation. So if you, for instance, you're 1 meter or 2 meters away from each other, but you're not facing each other, the likelihood of infection is not the same as if you're talking to each other. So there's a study showing that if you're talking, you're at a higher risk than if you're just in front of each other or crossing by. And our technology is able to do it. So we shared the code that you can actually run it on your iPhone, on any camera, and you have a way to measure if humans are actually respecting social distancing, or if they want to get a feedback, visual feedback of the situations. So that was perception. Now, sorry, I went a bit fast. I want to talk about what we have done or how our work has impacted the acting pillar. So in acting, so this is also quite a popular field in robotics. There is a lot of work in human-robot interaction. And one actually nice way to deal with it is this recent work from actually MIT, where they won the best paper award for that, which is learning a representation and then having a reinforcement learning framework to basically give feedback of what's the best representation to solve this task. What they missed is they actually only looked at human and robot interaction. And we showed that you need to also model human-human interaction into this framework. And by doing that, we were able to basically outperform their work. And this is again thanks to our social forecasting pillar, which allowed us to better think of how to model social interaction between humans to have a safer planning and acting pillar. This line of work still has some limitation. Whenever you do reinforcement learning, you usually deal in a simulated world because obviously you cannot run it in real life. So you have a bit of issue with this bias coming from your simulator and the real world. So one way that we want to actually address this bias is to have this unified framework where we want this latent representation Z to not only basically do the acting job thanks or be supervised with a reward coming from a reinforcement learning task, but still also from our supervised forecasting task. So can we basically have a unified framework that we are learning a shared representation that can be actually supervised with reinforcement learning, but also with our forecasting task. And we are hoping that by doing that, we will be able to actually address the sample inefficiency of our reinforcement learning framework and also this bias that is coming from simulation. We have, I have some also other videos here. This is our robot going out on campus, and this was a special day. We had some visitors. It was not, we were not expecting that, so I was quite stressed when I saw all these kids. I was not so sure how well we would do, but I'm quite thankful everything went well. And we were able to show that the robot is still able to actually plan its path according to this crowd. I think I have a few minutes left. I wanted to share also where we are going. So I've shared with you these pillars, how we want to push the limits of each of these pillars. But I also strongly believe that there might be a room to even learn a universal representation that is able to do all these tasks jointly. So all perception, forecasting, and acting. And one motivation is that, in fact, even to perceive, there are these intuition that basically the evolution of biological system can be driven by aiming to optimize storage or the use of meaningful information by learning to predict it. So maybe the way we encode the world, the current state, has been optimized in an efficient way that has the capacity to predict what's next. So if I have learned a representation that can predict the future, maybe my representation is good enough to even understand the current state, to even detect object. And this is what we are interested to study and see if this paradigm is true, and if we can show that there is actually a gain in doing all this jointly or having a shared representation for this task. Moreover, one of the biggest challenge that we need to face is robustness. So we are building intelligent systems, we are building real systems, and these systems will coexist with humans. These systems need to be trusted. These systems need to be robust to all type of scenarios. And so we are also right now studying if there are adversarial inputs to our system. So you might have heard that it's quite easy to actually perturb or, a neural network to solve a classification task. For instance, you can inject some noise that are not visible, but then they will fool any prediction model. what we are interested is, do we have basically inputs that are physically possible? That could fool our basically prediction tasks. We are also actually right now studying any risk behind the data distribution. So in machine learning, usually we are quite good into learning our model within a specific distribution. So what if our test sample are not drawn from the same distribution as the training set? What if the physical, what if it is physically impractical actually to collect a complete data set covering all the scenarios, all the world distribution? So this is what we are right now quite excited to study, this out of distribution extrapolation. And I can give you actually a concrete application. In fact, I've shown you these algorithms that are able to detect humans in 3D. So given this image, we're able to actually detect how far are these humans. So these numbers are the distance of humans to the car, to the camera. And the ground truth, and the way we actually are able to train this, we had actually the ground truth 3D, and the ground truth 3D is coming from an expensive sensor, a LiDAR sensor, that is accurate only up to a specific range, and in this case 20 meters. After 20 meters, we don't have actually good measurements. We don't have any label. So if we train our model to do this task, we can only detect humans up to 20 meters, and that's not good enough. How can we, given this data, also have our model that will work beyond this 20-meter range? And very recently, over the past month, we came up with a new algorithm that is able actually to solve this, is able to do this extrapolation task. So if you're interested, I don't have time to talk about it, but if this is a topic that you're also interested, feel free to come to me. We are quite excited about this, this line of research. So to conclude, thanks to the data that we have, we can propose new learning framework, and we can augment AI with social intelligence. We can shed light into the science of human social interaction and enable a safe yet efficient autonomous vehicle in our daily life, intelligent systems in our daily life to basically maybe make this future a soon reality. We are sharing our code online, so this is everything towards open science. So we are not allowed, don't let the student to publish without putting the code online. And we also are basically teaching about this deep learning for autonomous vehicle, how this data-driven method can impact autonomous vehicle. I was quite excited because we're able to run this first human-robot tandem race. So as part of this class, the students had to develop the deep learning algorithm that will allow the robot to detect an object and track the object. And they were in charge of basically running a race. And I have some videos showing you this race. Let's see if it works. This was in architecture, SG. So I'll stop it. So the video was made by our colleague at ENAC, so that's why it's a bit Hollywood style. I want to end here. Thank all the lab members. Obviously, this is the work from all these our students. I want to thank our collaborators and answer any questions if there are.
Doesn't look like. So, dear Alexandre, many thanks again for your talk today. Dear all, many thanks for your interest and participation. Please allow me to say some words of closing of the session. I promise it won't be long. So the next seminar will take place on June 29th at 3:15. Further details, including Zoom link, will be shared in due time. Please let me know in case you would like to present your lab's activities during one of the next seminars. And please kindly note that next Monday, this is 22nd of June at 3:15, we are looking forward to welcome Professor Jean-Philippe Vert, a research scientist at Google Brain in Paris and adjunct researcher at PSL Mines Paris at the CAS Colloquium for his invited speaker talk entitled Differentiable Ranking and Sorting. Looking forward to welcome you all soon again. Stay safe and goodbye.
Bye-bye, see you.
Thank you, bye-bye.